And so just to show it to you, let's now see what it can do. Let me introduce Mike Houston. Everybody give him a round of applause. Mike heads up the development of our neural net. And Mike, what are you going to show us today?
So why don't we start with the Kitty data sets. This was developed with Karlsruhe and Toyota. And so it's one of the standard data sets that's used to test the ability for things to detect objects. There's also a few other parts of the data set for things like object tracking, depth estimation. So we took NVDriveNet and we trained it to excel at doing car detection. So here's the raw output. There's no tracking, no other computer vision techniques. This is raw detection per frame. So you can actually see how stable the detections are. And with a few extra steps, this can be turned into a production network with things like tracking. So the training set that we used has 7,400 images, and there's 33,000 unique objects, unique cars that we're given to train with. So how this works is that 7,000 images isn't enough to really train a very deep network. So we take many, many rounds through the data, and we add forms of randomization to the data. So we'll do things like crop and warp and stretch and manipulate color space to help make a more robust network. We can train this network actually overnight with the data set provided, and this is the result that you get. So as Jensen said, it's been a few short months. Thankfully, we actually had two teams competing against each other internally on the network using slightly different techniques, and this is the result that we get. But we can take it a step further. So the neat thing about how neural networks work.
Now, before you go any further, Mike, so the first thing is you train the network, and it takes about a day. And if it had no GPUs inside, it wasn't GPU accelerated, it would take about a month. But the initial data set you trained with, how did the network that you started with surely wasn't trained to this level of capability with just a few thousand frames and a few thousand images.
Right, so we start actually by training a very large data set. So we actually start with the ImageNet data set, and it trains a very, very robust feature descriptor, much better than you can get by hand.
So this is 1.2 million images that we trained the network with.
Correct.
And it's trained to recognize about 1,000 different classes, different things.
That's right.
Right,
so we take those actually 1.2 million objects, but it's actually not enough to get the feature descriptor hardened enough. So we actually manipulate that to make it look like 120 million objects to train with.
So you trained this network with 120 million objects, and it took about a month to train on a GPU accelerated server.
That's correct.
Mm-hmm.
Okay. And so
now, just pause there for a second. It took a month to train the original network with the ImageNet data set. Without GPU acceleration, that month would have been a couple of years. Reducing it down to a month so that we can practically train the original data set, the original neurons and weights and the parameters, so that it could be now used for this new set of data so that it could be trained to enhance for this type of application. We had to start with a pretty robust network to start.
Yes, I mean, so the basis of our network was actually one of the winners from last year, one of the Inception networks. And I mean, this dominates the rest of the old computer vision approaches. So that's where we start with. But because we built such a robust feature descriptor, we can now retarget it for other similar applications. So instead of doing classification, we can use that same feature descriptor and now teach it to do detection very robustly. And there's just minor modifications for the network. But now what's cool is once we've done something like this, which is a single class-based detection, we can now do something much harder that actually isn't more computationally expensive because we already did all the work, all the initial learning in the network. And so we can retarget to a multi-class data set. So this is an upcoming data set that will be publicly available soon. It's the Cityscape data set. It was developed with Daimler. So there's more training images, and they're very, very finely segmented and detailed. It's a very modern data set. So we took that same network that we used for the Kitty data set and pulled in this data and retrained. And because we can retrain so fast, we're able to iterate very quickly to end up tweaking sort of the algorithms and how we set up the neural network and exactly how we train to get these types of results. So we trained for 5 different classes here. So pedestrians, street lights.
So not one engineer coded something to detect a man walking across the street in a suit.
That's right. It's
2 ladies walking down the street. Not one feature detector was coded by hand.
Correct. It's basically like holding up millions and millions of flashcards to the computer and telling it to learn, and basically nudging it in the right direction when it gets things wrong. So besides even the classes, we also had to train the tightness of the bounding box as well. So this is all work in progress, and it was done very, very quickly. But as you said, because we're not having 300 engineers sit there and hand code features, we can turn around and experiment so fast. Basically, you're now using compute time, which is relatively cheap compared to engineering time in order to do these experiments. So we can turn things around very fast. So the Cityscape data set is actually initially designed as a segmentation data set. So imagine basically hand coloring in all the people or all the cars and things in the data set. So again, we took what we trained here and we turned it over into a segmentation network, as Jensen said, where we do per pixel labeling. So we can switch and show you the results of that. So this was done with only a few days of research and training, but it shows that how quickly you can turn things around.
So in this particular case, not only are you detecting a car, you're detecting all of the pixels that are associated with the car.
Right. So where this gets important is if you think about needing to calculate free space in the scene. So it's sort of like if you ask a child to take a crayon and say, color the road. Color things I can drive on. Okay, color the people, color the cars. And so this gives you the next level of perception, saying, well, what can I drive on? What is this thing at this pixel that I'm looking at? So it's a much more robust way to handle perception in a car. In a practical solution, you're going to combine all these techniques.
And this is still the same core network. We taught it to recognize one thing, and then we taught it to recognize more than one thing, and then now we're teaching it to recognize which pixel associates with what thing.
That's right. So once you can train a robust enough initial feature descriptor, then everything becomes a fine-tuning exercise. So anything that's visual, we can retarget very quickly into detection, segmentation, multi-class, a bunch of other things. Now, to really show the power of this, though, so these were more of our research exercises on sort of research data sets. But we had an OEM, Audi, who was nice enough to actually give us a really challenging data set. They wanted to see, could we really make neural networks work in very difficult situations? Because this is one of the things where if you are an engineer and you're trying to hand-tune those features, it's just brutal to deal with really difficult visual conditions. So if we look at the data set that Audi gave us, so we trained, they gave us 27,000 frames and 120,000 instances of vehicles to train on. And so we picked one of the more challenging data sets. This is in snow with road spray coming off the road. Again, there's no tracking or any sort of any gains here. It's just raw detection every frame. And it was actually the point where there's that third car there where we actually thought we had a bug in the network because as humans, we struggled to see it until we closed much further down the scene. And the idea of trying to hand code features or even use very shallow machine learning to be able to capture some of the difficulty here is just daunting. It takes a lot of time. But again, we're able to take the data from one of our partners, take our network, and retarget it overnight to get to this quality. Okay? So there's still more work to go and higher resolution and more speed, which is why we need all the horsepower that we're about to put in PX2, so that we can run more cameras, higher speed, and even deeper and fancier networks to get better and better at our ability to detect difficult scenes.
That's really amazing. Thank you very much. Good job, Mike.